Hello students, welcome back. We still have one more topic to go in section 4. It's an optional topic because it's rather advanced, but here it is anyway. It's the very last subsection here, theory of interval estimation. Let's begin with a motivating picture, and here we go. The visualization of confidence interval. So here we have apparent probability distribution of population mean mu centered around the best point estimate, x bar, the sample mean. Now, it is more likely that the population mean mu is relatively close to the sample mean x bar. So as you can see over here, we have higher probability density around x bar. You see, probability density, y-coordinate value is higher around x bar. And if you move far away from x bar, either to the right or to the left, the probability density goes down. This is a normal picture because of the central limit theorem, and symmetric, unimodal, and so on and so forth. And then we can do the z computation through the standardization theorem, and we can do all those computations. Everything works out fine as far as the computation is concerned. But in terms of theory, there is a bit of a problem here, because the population mean mu is not a random variable. It does not move around. On the other hand, the sample mean x bar, this isn't a random variable, it changes. So if you take a different sample, then it's quite likely that sample mean x bar will change. And then if you change another sample, then it may change yet again. So x bar value is moving around, but looks like it is fixed at center right here. Mu is not moving around, but looks like mu is distributed around x bar in terms of probability distribution. So something is wrong here. As far as theory is concerned, we know the computation works, but in theory, something is amiss. How do we make it right is the question. And I explained those through motivation 1 and motivation 2. Motivation 1, mu is not a random variable. It doesn't move around, but look at the previous picture. It looks like mu is moving around and you have a probability distribution around x bar. Something is wrong. Motivation number 2, we have central limit theorem, and that says the sampling distribution of sample means, x bar, is distributed around the population mean mu. So centered at mu with the standard deviation, which we call the standard error, sigma over square root of n. So center should be mu. But apparently, from the previous picture, it's not what we did. How do we make it right? And we can use this kind of idea. From the central limit theorem, we get the sampling distribution of sample mean, the distribution of x bar, which is around mu. And then we use geometry, the symmetry of the normal picture, to get the other way around. And this transition is related to a change of reference frame. For example, let's consider this example. You are driving on a highway, a straight highway through a car, and then if you look at outside, then it looks like the trees are moving backward. And if the observer is on the street with a tree, then trees are stationary and the car is moving. Which is right? In terms of Newtonian mechanics, they're both correct. And that's the kind of analogy we can choose. So here, we have probability distribution from the stationary point mu. So observer is now outside on the street, and trees are staying the same, and then the car is moving fast this way, positive direction. Now, if the observer is in the car, then the street and trees are moving backward. As you can see, we have negative side. And as far as the speed is concerned, without the direction, just speed, the magnitude only, this area, this probability, and this probability here, they are the same. So it is basically a change of reference frame, whether you look at the world from the inside of the car or outside, which is stationary, which is moving, and are they really the same? Well, we can explain those through these kind of pictures. Here we have previous picture, and then we superpose both of them. Let's see, let's get all those in the same viewing window. Okay, these two, superpose them, and draw the reference frame around mu, that is outside the car in stationary position, or you can consider the reference frame in the car. Observer is now in the car. And then, are they really the same? Yes, because of the symmetry. Let me show you. Let's get the graphics. Okay, here we go. This part here is the same as this right-hand side part because of the symmetry of the normal curve. Make sense? That's coming from the symmetry. Now, we take parallel shifting. This red is same as this green because of symmetry, and then we shift it. So this green is the same as this blue. So symmetry, and then parallel shifting. We can do the same thing from here as well. We start from this blue here, and then use the symmetry to reproduce the same area here to the left. Again, it's the symmetry. And then take the shifting. Shift this green to this red. So they're the same probability. Now, do they make sense? You can do the same thing the other way around. In short, yes, it is okay to draw the picture like this, as you did in 4.2. As if mu is moving around x bar. Basically, it's the same as the change of reference frame. So here, observer is in the car, which is moving around, and consequently, the trees are moving backward. So depending upon which direction the car is moving, tree could be backward, here, or there. So that was the final piece of puzzle. If you understood everything, that's great. If you didn't, and also if this physics analogy, Newtonian mechanics analogy didn't work for you, sorry about that. That's the best analogy I could find. Anyway, that's it for section 4, and we're going to talk about section 5 in a separate video.